Good afternoon, everyone. Well, at least afternoon for me. I guess it kind of depends on when you're watching the video. Once again, I'm back. I'm going to be talking about another topic of Calculus BC's final section. In this case, we're going to be talking about, I guess I'll call it like our first two official tests to determine convergence, or specifically today, divergence for sure. So, giving you an update, for me it's Tuesday. So things that are exciting me today, other than the potential free agency of Tom Brady that suddenly opens up the AFC East if you're a sports fan. I'm excited about this coming in the mail, getting a video game. So I'm wearing my baseball gear since opening day may actually be in June if it happens at all. So I'm trying to, stay patient, and at least the Oakland A's will be able to pursue the World Series electronically for me if I can get myself to play video games, which other than Pokemon, I really haven't played much in the last couple years. Having said that, though, obviously, thank you for continuing to watch. Hopefully you're learning some stuff, keeping your mind off things, and giving yourself a little bit of time each day to do a little bit of math and some analysis and some thinking to, keep those skills going and to keep yourself occupied a little bit. So as I've done before, I'm going to continue the same basic process that I have up to this point. I'm going to work through the material. I've kind of broken it into chunks. There's kind of an opening one here we'll talk about. You can see it already on the front page. And then after that, we'll give you some time to work through a short try-it that I've set up using QR codes. Thanks to a suggestion from a student, I'm going to actually do written solutions for the try-its in case when you go to do them on the Google form, you just don't feel like you understand exactly what happened. So I'll start doing the first 2 days. I guess there were 5, I think, from the first 2 lessons. I'll do those and post those as well, and then for these I'll post them as well. I won't do the active solutions in the video just for the sake of time, but I will post them later on. So you'll have access to solutions in addition to, of course, checking your answers on the QR codes or on the links themselves. And just like before, those links to those try-its will be in the description as well as available via QR code, which each one has. Finally, the last thing I'll say is kind of interesting. Trying to occupy myself. I was watching the 4th season of Rick and Morty for, I think, actually the 4th time, interestingly enough. And I actually found a QR code in the middle of the 2nd episode. And I used my phone to pull up the QR code and see what it led me to. And it led me to a Rick and Morty fan shop where you could buy the literal hat that had the QR code on it. So I don't know whether to be proud of myself or a little embarrassed of myself for freezing my TV for more minutes than I'm proud of to check what that QR code led to. But I was excited. Same way whenever a movie comes up and I check and want to figure out what the phone number actually leads to. So just there it is. There's something to throw out there to keep things a little bit light. As far as the math that we're going to work through, as it says in the title today, we're going to be testing for divergence. Truthfully, that title is kind of a misnomer. It's not so much that we're going to purely be testing for divergence, but the big new test that we're going to get today is, in fact, based on divergence. In fact, it will only tell us whether or not a series diverges. It won't conclusively tell us whether a series converges. But the other one is going to give us both convergence and divergence, and in fact, it will be the last one of these techniques that we see where we can actually figure out the value to which those series converge. So truthfully, if I was going to title this, something less catchy than testing for divergence, I'd call it geometric series and the nth term test as the 2 separate tests that we're going to use. And you'll start to notice today that I describe things as tests over and over again. These aren't your in-class assessments or exams or some sort of summative or formative assessment. These are just tools that we use to determine whether or not a series converges or diverges. And the focus of the rest of this kind of unit that we're working on is going to be on using and developing certain tests that we'll be able to use on particular structures of series, so we can determine whether or not they converge or diverge, which will pay off in the future for units that are more meaningful than just does this converge or diverge. Alrighty, so I've said enough. Let's jump into the lecture and actually take a look at things here. So on the first page, as I mentioned, there's kind of a short starting spot here. The first thing I wanted to throw out there were a few properties of series that have been addressed in previous courses before, possibly in your honors pre-calc course or your accelerated math course, likely in Calculus AB as well, particularly before we did Riemann sums, which use sigma notation. But there are a few properties that series have, and these properties hold for both infinite and finite geometric series. So what it says in our properties here is if a series sum of the terms of the sequence A sub n converges to capital A, and a series sum of the terms of a sequence B sub n converges to capital B, then these 3 properties hold. And again, hold your applause. I don't think any of these are particularly mind-blowing on their own. So the first one says that the sum of k times a sub n, meaning that we're multiplying all the terms of a particular series by k, converges to k times the sum of the series. It's like you can factor out a GCF of k, add up all those stuff just like you did before, and then multiply the result by k. Very straightforward to think through. If you need to kind of look at an example or think about it a little bit or just kind of stop, you can probably make this work out. But the first one is a scalar multiple property of series, or I should say convergent series. The second one says if you add the terms of the two separate sequences together to form a series that sums up those two things, the sum is just the sum of those two series. And then third, it says that if you take the difference between the two series, of course the final sum converges, or the final series converges to the difference of those two series. Now something you might notice here is that it does not say that you can multiply two series together. And that should be very true, and the biggest reason I can describe without going into a ton of depth is simply that if you tried to multiply two series together, you'd have a whole bunch of terms times a whole bunch of other terms, and you'd have to multiply all of those terms towards all of the other terms. It'd be the most massive distributive property task in the world, especially if they were going on for infinity. You'd have infinite terms to multiply by infinite terms. So of course it doesn't work for anything beyond addition and subtraction, as well as scalar multiplication. But I just wanted to establish these properties because there will be some times where you're given some things, and I want you to be able to use these as you'd like to. So again, that's just kind of a brief introduction with some properties of series. Nothing that you're going to be, that you'll have to practice here, but just kind of a quick introduction to remind you that series do behave in a really nice way. Okay, having mentioned those properties, let's instead jump into the first major section of today's lesson. And that is, of course, geometric series. Now, we talked about geometric series a little bit in the second lesson, yesterday's, and we talked a little bit about the ideas behind a geometric series, and in particular looked at finite geometric series. But the question that we want to talk about today and tackle is infinite geometric series, and how can we determine very quickly, based on properties of the series, essential properties of the series I might say, that a particular infinite geometric series is going to converge or diverge, and is there ever any ambiguity? So we can answer all those questions for you. Before we dig in too far though, let me start by just kind of establishing some formal criteria for a geometric series. So again, we've defined these things before and said it's a pattern of multiplication and talked about how a series is adding up the terms of a sequence. But just to illustrate what this would look like, a geometric series will always be of the form that we'll see right here. There's a first term, then that first term gets multiplied by some common ratio r. That is the ratio between consecutive terms that we used in our definition earlier. Then the next term would be the first term times that ratio twice, then the term times the ratio 3 times, on forever. And if you wanted to formalize this, by the way, I believe this would be written as a sub 1 times r to the n minus 1 plus dot dot dot. That way you can see the general term written in there just for clarity's sake. So in here, this is an infinite geometric series, but of course we talked about a little bit yesterday that there were finite geometric series that you might possibly run into. And it's perfectly fine, to I should. Okay, now I'm not allowed to press that again for using finite, so we should be fine. Okay, I won't do it. So anyway, if we're looking at a finite geometric series, the sum is given by the following expression. We would say the sum of the first n terms of a geometric series, that's general like the one we see up top. That finite sum of the first n terms would be the first term times the quantity 1 minus the ratio to the nth power, all divided by 1 minus r. So I bring this up to start with, not because we're going to be dealing with finite geometric series very much, but simply because it's important to establish, because it'll allow us to start to build towards our infinite geometric sum. So for a moment, let's harken back to the work we did yesterday and think about a situation that we saw. If you'll recall from that lecture, we talked about the series 1/2 to the n, which written out is 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 dot dot dot. So basically we talked about this one. And if you'll recall when we did it, we illustrated the convergence of this particular series by illustrating it geometrically, or sort of graphically, but mostly geometrically. We added 1/2 of the rectangle, or shaded it in, then we shaded 1/4 of the rectangle, then 1/8, then 1/16, then 1/32nd, then 1/64th, then 1/128th, and then at this point it was very clear that it seemed like this series was approaching a sum of 1. I guess you could say one rectangle, but the idea is there. We're approaching something there, which indicates that this particular geometric series, 1/2 to the n, where the ratio is 1/2, is going to converge. And in fact, that's not a coincidence. In fact, this sort of filling in possibility is not always easy to illustrate geometrically or graphically, but it is true. In fact, the defining characteristic of a geometric series that determines whether or not it converges or diverges is basically that common ratio. So to help us here for just a second, let me write out a statement here. Basically, if we want this series to converge, we need the common ratio to be small enough that it's going to slowly fill in some sort of rectangle, even though, of course, negative ratios might cause some problems. So the characteristic that we're looking for is this. If the absolute value or magnitude of that common ratio is less than 1, which we could call like a small enough ratio, but if that's true, then something interesting happens here. So if your ratio is less than 1, then as n goes to infinity, so in other words, as you multiply that ratio more and more times, then what's going to happen is you're going to get r to the n approaching 0. Now let's think about that in terms of r equaling 1/2. So let me just pause for a moment and take a look at what happens if r equals 1/2. The reason that this is true is, think about it this way. If we take 1 over 2 to the n, that's the same thing as 1 to the n, or 1 over 2 to the n. If n goes to infinity, then that means that, here, let me write this on another line, sorry. In fact, I don't even need that parenthesis. Let's just get rid of that. So what's important to note here is then, as you take n going to infinity, then you're going to have 1 over 2 to the infinity, which is 1 over infinity, which is 0. So what you can see, everyone's making so much noise right now. Go figure. So as n goes to infinity, we can see that with that smaller ratio, when you constantly multiply that thing that's smaller than 1 by itself, you slowly approach 0 as you get more and more terms added in there. So the idea is, if that happens, look at what happens to our original finite series sum. In fact, you know what? Let's be clever about this. Ah, shoot. Oh, are you kidding me? Really? Really? Okay, whatever. It's not that bad. I feel powerful erasing that rectangle. Okay, so what we're going to do here, what I want to point out, is that if we instead think of this as an infinite sum, look at that cleverness, that was me planning this whole time, infinite sum, then instead we'll have the sum with an infinite number of terms, and that means the only n that we have in the problem will become infinity. But here's the thing. If r's magnitude, in other words, that common ratio, is less than 1, we just saw that r to the infinity is equal to, or at least approaching 0. And what that means is that our sum, which some would call s, would be a sub 1 times 1 minus 0 over 1 minus r. And what that gives us is the sum a sub 1 over 1 minus r. I'm just trying to make sure that it's there. And this value is the value that an infinite geometric series converges to. The only requirement is we have to have the magnitude of the ratio be small enough. In other words, we need a sufficiently small r so that way we can actually make sure that the series converges. So again, this is a very technical and kind of detailed and using limits and stuff kind of approach to this, but it basically leads us to something that we can use to test a geometric series. And then not only that, but since this expression is the sum that a geometric series converges to, we can actually find the value to which a geometric series converges, assuming that its ratio is sufficiently small. So this brings us to what we're going to call the geometric series test. And again, it's one of those corny names because truthfully this is just how we talk about geometric series. We just kind of talk about them as whether or not they converge or not based on the ratio. But the idea is what you see right here. Let's see, do I have anything to add? Cool. So it says for infinite geometric series. So things that are worth pointing out here, especially if you're kind of taking notes as you go. For an infinite geometric series, like with those terms being added up, again multiplying by common ratio, a sub 1r, a sub 1r squared, etc. If the ratio is greater than 1, excuse me, I said the ratio. If the magnitude of the ratio is greater than 1, then we'll say that the series diverges. And again, I'll show you why that is in just a second. On the flip side, using what we just saw, if the magnitude of the ratio is smaller than 1, meaning that it's smaller than 1, so when you multiply it by itself, its magnitude keeps getting smaller and smaller, then the series converges. And, super cool, the sum is actually this guy. So we can actually figure out what that sum is every single time. So now, before we talk about that, and before we do some problems to work through here, it's important to note a couple things. First, since I've already talked about this a little bit, let me steal this really fast. So let me just throw that in there. For the second option that you see up top, when you see the second one right there, this guy is basically the property that you see right over here. This is that process. Basically, because the magnitude of the ratio is small, we can imagine it slowly filling things in and approaching something really, really nicely. On the other hand, the first version right up top, this guy, this situation might not jump out at you because it might just not seem like it's going to work out that way, or why is it that it can't? And the idea is this. I'm going to try to use this down below with similar colors. Let's say that we have a geometric series whose ratio is greater than 1. So setting aside for the fact that it could be negative or positive, in other words, switching or alternating the signs of the terms, what that means is that as we go forward, no matter what a sub 1 we start with, we're going to have something bigger than a sub 1. So whatever a sub 1 was, we're going to add something bigger to it. Then from there, we're going to add something bigger than that previous term to it, because again, its magnitude is greater than 1. Anytime you multiply by something greater than 1, it just keeps growing in size. And what you'll notice is the more we add here, and obviously this is an exaggeration, it's hyperbole, it's happening really fast, but the idea is when you keep adding bigger and bigger things, all that can happen here is that, well, okay, I've used too much space, I don't have room to write anything. But as you keep adding bigger and bigger things, even if they're alternating signs, what that does is it causes your sum to approach plus or minus infinity. In other words, it diverges. And that was kind of the entire thing we were looking for, was a criteria in which we could use to determine if a geometric series diverges. So the idea is if r is bigger than 1, the term's magnitudes just keep getting bigger and bigger, and our sum has to approach one of the infinities. And that is, by definition, divergence, more than anything else. Except for that book that featured Triss and 4, I think, were the characters, and that had 2 great first books, solid first movie, and then was the worst book I've ever read in the third one. Is that slander to say? No, I felt like it was true. Whatever. So anyway, there's our stuff. So there are 2 criteria. It turns out that all that really matters for us is to determine the ratio. That's what the geometric series test amounts to. Can you figure out what the ratio is of this geometric series? And then play along from there and see what happens. So since we're just kind of bringing this all up, I want to, of course, work through a couple examples and talk through it, but I don't think you're going to find these to be particularly difficult. Instead, it'll be some of the more interesting questions we get to that'll challenge you a little more. Still, I'll start with the basics, though. Oops. So first and foremost, we want to determine the convergence of this particular series. So we're trying to figure out, does this geometric series, or assuming the series is geometric, does it converge or diverge? We say determine the convergence of, just because that seems to be our common thing. So what we're going to do first is we're going to begin by identifying what type of series this is. So I'm going to start by noting that this is a geometric series. And you can write geom if you want to, just because, we got a lot of time right now, but theoretically we don't have that much time. So I'll make note that from looking at this expression, I noticed that it's got something times something to a power. So basically it's a constant number to a power, which means we're multiplying the same thing over and over again, which tells me that we have a geometric series. In particular, though, this geometric series has a ratio. That ratio is whatever it is that we're multiplying over and over again. So right here, from looking at the structure of that summand, that's the thing inside the summation, we can see that the magnitude of r is going to be 4/3. Now at this point you ask yourself, does that ratio have a value greater than 1 or less than or equal to 1? Or excuse me, greater than or equal to 1 or less than 1? And the answer here is clearly that's greater than 1. Given that, since we've just shown that the magnitude of the ratio is greater than 1, according to our system, In fact, by the way, I should have added something here. In fact, I'll add it right now. Boom, it should be greater than or equal to 1, the series diverges. But besides the point, what we noticed is we now have a situation where r is greater than 1. That tells us that the series is going to diverge. So right there, we can then say, therefore, our series diverges. In fact, you know what? I'm going to be more specific. I don't want to just say the word diverges. I want to be, well, I'm going to be cheap at this point, and I'm just going to bring this down because, like I've said before, well, you don't want to watch me just write out a series all the time. So therefore, the series diverges. And then we could say it diverges by the geometric series test. But typically with geometric series, we don't cite the test by name. We just say, as a geometric series. So again, we can abbreviate that as geom, as a geometric series with absolute value of r greater than 1. And this gives us every single thing that I'd be looking for were I scoring your work. I'd want to see noted that it was a geometric, here I'll use a different color, I'm sorry. I want to see noted that it was a geometric series. I want you to correctly identify the ratio. Then I want you to state correctly that it diverges, in this particular case. And then I want you to cite the test with a reason. And our reasoning was, of course, given other places, so that last little bit wasn't there, but we described what it was. Alternately, you could also say this, assuming that you did the work in purple, you could also say that the series diverges by the geometric series test. That would be acceptable as well. It's not my favorite way to do it. It's a little bit clunkier, but at the same time, perfectly appropriate to say. So your call, be you. There's 2 different ways you could handle this thing. And again, this last one is assuming that you wrote this. So I'll make note of that as well. Assuming you wrote this. So basically you have to identify the ratio somewhere in your work in order to get credit. So cool stuff, pretty straightforward. Likewise, we have a second geometric series for us to look at. And again, as I look at this structure for the first time, you can be fooled a little bit, but again, it clearly matches the structure we're looking for. We're multiplying by something over and over again. I can see it because we have a constant raised to the n-1 power. We're multiplying by 21. This one's kind of interesting though. It doesn't start at n equals 1, so that may play a role. We'll see what happens. But based on this, we can definitely recognize that this is geometric. So we can say, just like we did on the previous page, that this, based on its structure, is a geometric series, which I'll again abbreviate because I'm a lazy human. It's a geometric series with the absolute value of r equal to, let's see. Well, according to the structure that I see here, it looks like the absolute value of r will be the absolute value of -1/2, since that's the thing being repeatedly multiplied. So the absolute value of -1/2 is 1/2, which is less than 1. That is enough for us to, just like before, draw our conclusion. So just as I did on the previous one, let me do something kind of cheap and bring this thing down. Let's see. Boom-ba-doom. So, boom. Oh, why did it not? Oh, I felt like it saw me. There. So, from here, we can say, therefore, the series in this case, because its ratio is sufficiently small, the series converges. And then you could say by the geometric series test, and as a geometric series, with absolute value of r less than 1. Now, having said that, this is a good explanation. We definitely have identified whether or not this geometric series converges, but the only issue here is that because it's a convergent geometric series, we actually have a little bit more. We can actually say the precise value to which this series converges. And we don't want to leave that off if we have the opportunity to get it. Again, we're going to need to cherish it while we can because we're not going to be able to in the future. So what I want to do in addition is I want to figure out what is the actual sum that this series is converging to. And I'm going to use that a sub 1 over 1 minus r formula to get there. Now, as you jump in, some of this is really easy. It's very easy to see that in our denominator, we're going to have 1 minus a -1/2, which will give us something over 1 plus 1/2, which is something over 3/2. So definitely true. The only thing we have to be careful with, though, is that our first term isn't necessarily going to be easy to find. So keep in mind with this particular series, because of the fact that we started at n equals 0, our first term is actually going to be 21 times negative 1/2 to the 0 minus 1. So that 0 forced us to include that 0 for our first term's n. Now, having done that, we've got a little bit of extra work here. We have 21 times negative 1/2 to the negative 1 power. And if we follow that, negative 1/2 to the negative 1 says to flip the value. So, or to take the reciprocal of the value. So this will be actually 21 times negative 2 to the positive 1 power. And of course, 21 times negative 2 to the first power or not is going to be negative 42. So, problem clearly I wrote. Turns out the first term is actually negative 42 in this case. It was a little obscured by the way it was written in this case. But now that we have it, we can finish off the problem pretty easily. So given that we have negative 42 over 3/2, that's the same thing as negative 42 times 2/3. If we simplify this out, that becomes 14, and we get, it looks like, negative 28. So not only does that series, the geometric series, converge as a geometric series with sufficiently small ratio, it converges specifically to negative 28. Meaning, if we were to look at more and more terms of the series, theoretically the term should get closer and closer to negative, or sorry, the sum, not the sum, I said that wrong. The sum should get closer and closer to negative 28. So before we take a moment to look at some other things we can do with geometric series, let's see if that actually looks true. Let's go to Desmos and see what happens. So there's Desmos. We had the sum from 0 to, and I'm going to put k in here. Sorry, let me just do this trick that I've done a few times. You should have that done ahead of time, but I always forget. So we'll go from 0 to 100, steps of 1. Okay, so in our series we had 21 times negative 1/2 to the n, another trick. Okay, so it says with one term we have, all right, k equals 1, we have negative 21. Let's see what happens if I put in 0. Okay, cool, it works. Okay, so as far as, oh, that did stuff. Okay, sorry. So let's see. As we add more and more terms, does it seem like it's getting closer and closer to negative 28? Now, interestingly enough, it might have looked a little dubious at the beginning, because notice how it's like going negative 27, negative 28, negative 27, negative 28. But that's because this is what's called an alternating series. Because the ratio is negative, it keeps changing the sign. So we get these kind of values that are kind of oscillating back and forth around the value we're converging towards. But once we get here, you're starting to notice negative 28.000000522. I bet. Yeah, look at that. Once we reach 40 terms, once we reach 39 terms, the Desmos can't even tell the difference between its sum and negative 28. So I'd say that's a pretty good indication that that's getting bigger and bigger in the way we want it to. Contrast that, by the way, with the first problem that we did, which I believe was, oops, this one. What was it? To the n minus 1. Take a look at this guy. If we add up more and more terms, the sum just keeps growing. It's just bigger and bigger and bigger, because obviously that is a divergent series. So you can see that there is a difference between those two. Probably should have done that earlier, but at the same time, what's it doing? There we go. So kind of cool stuff. Let's see. I think I'm going to pop that into the notes because I'm proud of my work there. Boom. Okay, so we've seen some good stuff here. We've seen this work. We've figured out what value it converges to. Kind of nice stuff. So now before we get to practice with this, though, I just have one more thing I want to talk about with geometric series. And it's just kind of a neat quirk. Like, I consider it kind of a little bonus. And actually, the truth is, for those of you that have been involved with Mathletes or done some of the contests, the first year I taught BC, we had a number of students in my BC class qualify to take this contest called the Amy. Sadly, it was canceled last week because of the world for 2020. But at the same time, we had a bunch of people qualify. And it turned out that they all got a bunch of questions right on it, in particular because of a particular tiny skill that I included. So I told myself, as kind of to honor the good karma of that, I would always teach this little skill as well. So just so you can see, there's also kind of this neat little after effect that comes with repeating decimals. So right here, what I've got is just kind of a quick little investigation or explanation, well, called a demonstration that shows you that you can actually use this idea of an infinite geometric series, or more particularly a convergent infinite geometric series, to show that you can actually transform a repeating decimal into its exact rational value. So right up here, just so you kind of get an idea, we have a repeating decimal. It's 0.173173, and it repeats that 3-digit pattern forever afterwards. And our goal is to rewrite this as a rational number, a over b. So that's where we're going to aim to go. We're trying to get to exactly that. So thinking that through, and I usually use for rationals, I apologize. I usually use m over n. Sorry, could use p over q, but p's and q's kind of look the same. So here's what I'm going to do. This is going to be kind of weird the first time you see it, but once you've got the idea, you'll be able to very quickly do this, I think. So what I want to do first is I want to point out that the repeating section is 173. So that first section that I just highlighted in blue, I'm going to think of separately. That 0.173 is the same thing as 173 thousandths. And if you think about it, if you were reading that, you would actually say 0.173 is literally 173 thousandths. That's just what it literally is. Now, following that pattern, I want to look at this next piece, and I'm putting it in that kind of plum color. So if we think about that as separate from the blue section, we have 0.000173. Now that, if we're looking at it in terms of like its value, it's clearly the same 173 over 1,000. The only difference is we've multiplied it times 1,000 so that we can shift it further down the line. So that way we end up at, instead, what is that? Tens, hundreds, thousands, 10,000s, 100,000s, millions. Millions. $1 million. I have great impressions. So basically that gets us there. So we had to multiply by another 1/1000th. Having said that, we can go even one step further. If we look at the third set that's on there, and hopefully this will be enough for us to develop the pattern, that would be the same thing as 0.00000173. And that would once again have the same basic structure of 173 over 1,000, but in this case we'd multiply 1 over 1,000 a second time so that it shifts not just 3 units over, or 3 digits over, 3 decimal places over, but 6 decimal places over. Just keep shifting us down the line. And the truth is, the reason I bring this up is that what we're seeing is that there's a way of writing this decimal that you might not have expected right off the very beginning. So specifically, we can write the repeating decimal 0.173173173 onward. We can write it according to this work as, oh, are you kidding me? Oh, it's going to be so clever. Okay, well, forgive me for a second. My computer chose not to help me. I shall remember this grave error. Okay, it's chosen to be jerky. But the idea is this. If I take those individual terms that represent each like decimal chunk of what we were looking at, I'm hoping you're about to see what I'm going for here. Wait, does this one actually work? Oh, finally one worked. Heard my insults and it collaborated. So what I'm hoping you notice is that this is just another way of writing a repeating decimal. The difference is this is pretty clearly an infinite geometric series. Like, look at it. It's just an infinite geometric series because we're taking a first term and we're multiplying over and over again by a ratio. We're just multiplying by 1/1000th every single time. So it fits that form of a sub 1 plus a sub 1 times r plus a sub 1 times r squared. This is literally just an infinite geometric series. The reason I bring that up then is that we can transform it into a specific infinite geometric series. We can write this as the sum from 1 to infinity of what looks like 173 over 1,000 times 1 over 1,000 to the n minus 1. And according to this, because 1 over 1,000 is going to be our ratio, the absolute value of r is equal to 1 over 1,000. And that means that since it's less than 1, that means the series should converge. And specifically, it's going to converge to a particular value. It's going to converge to that sum we found earlier, a sub 1 over 1 minus r. So in wrapping this up so we can kind of see where this all goes, we can say that the sum is equal to the first term, which is 173 over 1,000, divided by 1 minus 1 over 1,000. Now if you clean this up just a little bit, obviously the numerator doesn't do much. It's going to stick around for a second. But that denominator is the same thing as 1,000 over 1,000 minus 1 over 1,000, which is 999 over 1,000. And having done that, if you rewrite this using the whole dividing fractions you multiply by the reciprocal, you'll get 173 over 1,000 times 1,000 over 999. And having said so, we get that this is equivalent to 173 over 999. So there is our m over n that we were looking for at the very beginning. And the way to get there was using infinite geometric series and kind of taking advantage of this formula we have. Now again, just because it's kind of cool, let's go check it and make sure it actually works out. 173 divided by 999. Look at that. Indeed it is 0.173, So it looks like we got what we were looking for. So good job us. Turns out infinite geometric series work really well for that purpose as well. Again, not a huge concept in the long run or in the grand scheme of things, particularly in this unit, but the kind of thing I'll ask you one question about on a test, just to, again, like I said, honor that first time I taught it. Having said that, this is a good time for you to actually try some of these skills and kind of work your way through infinite geometric series. The try it definitely doesn't require the same amount of depth as what I've just talked about here. I've kind of gone overboard talking about these things, probably because I'm kind of lonely and bored. But having said that, just a couple questions for you to look at. As with all the other try-its we've had so far, you can either click on the link in the video description to go test yourself on some of these skills, or you can go to the QR code if you're watching this on a computer and work through it right there. Both options are totally fine. And again, like the QR code or the Google form try-its are obviously encouraged. I think they're really beneficial, particularly as you're working through things. These also provide really nice stopping points, but it's completely up to you how you use them. Having said that, I'm going to take just a short little break, take care of a few things, and then I'll come right back and I'll work on the next part and let you work on that as well. Welcome back. Well, you probably haven't gone anywhere. I have. Boy, eventful last few minutes as I took my short break, which, by the way, if you're not clear why I took a break, I had to go to the bathroom. I'm home. I'm already walked, I think, 22 miles today, and I'm on my 64th ounce of water already, and it's like 4-something o'clock. But the big news while I was walking was that Sacramento County residents are now urged to stay at home to create kind of a shuttered society for the next few weeks, which is just kind of awkward to deal with and kind of difficult. Obviously, it doesn't mean we can't go to the grocery store or see people, or like I'm going to my parents for dinner later and checking on what groceries they need. But it's definitely a uncomfortable thing, but surely for the best, and definitely for the best. The other thing was that Cinemark theaters closed down, but I haven't gone to the movie theater in 2 weeks because of all these things, or a week and a half, whatever, week before it became serious. So in any event, there it is. Let's jump in and actually start looking at the math for the second part of this lesson. So it didn't move. Lovely. I'm a little shaken. So from here, where we're going to move on is, well, I'll put it this way. Like I said that we were going to focus on trying to determine some tests that would tell us whether or not a series converges or diverges. And the truth is what we're going to move on to is a test that only tells us whether a series diverges. Having said that, I will say that this is probably the simplest of the tests that we will see outside of course, the geometric one. Outside of the geometric one we just saw. It's the simplest test, but it's very easy to become confused on. So although I know some of you are going to be tempted after you see the next page and maybe look at an example to go, oh yeah, this is easy, I got it. I really encourage you to pay attention to the explanations I give and the stuff that follows me answering the question very quickly, because those reasons are the things you can kind of get into your head now to understand exactly why it is that this simple test means what it does. And truthfully, this is the one where people just kind of forget it by week 3 or by the 3rd standard quiz a lot of the time. So please do listen carefully to it and engage with it a little bit more than maybe you would normally, because although it's simple and easy to use, it can sometimes confuse people later on. So not to mention it's a difference between sequence and series convergence, so we'll talk about that. So to kick things off in the second section, which is eventually going to talk about something called the nth term test for divergence, I begin by presenting a theorem. And that theorem, which we will actually prove, in fact it's already proven on your screen and has been for the last minute or so, states that if a series converges, then the series... The theorem states that if a series with terms a sub n converges, then the limit of those terms, in other words, the limit of the sequence, is 0. So what this is telling us is that if your series converges, then it's necessary for the terms of the sequence to uniformly approach 0. So now to explain this with a proof, the proof may not be the thing that sticks with you, but I do want to at least talk through it once, and then I'll kind of write my little translation down there at the bottom just to kind of clarify things. But basically the reason this works is coming from the sequence of partial sums work that we did before. Basically, if a series converges, then we know that the sequence of partial sums has to converge to a finite real value, which we're calling L here. So in other words, the limit of that sequence of partial sums is going to be L. Well, having said that, if we take the limit of the sequence of partial sums, but we remove the final term, or we just don't include the nth one, and we instead focus on the n-1th one, well, we'll get the exact same value. We're still converging in the same direction. We're still doing the same thing. We've just removed a single finite term. So in other words, as it says below, the limit as n approaches infinity of s sub n-1, in other words, the limit of the sequence of partial sums less one term, is also going to be equal to L. They're going to be converging to the same thing. Then if we take things there, the difference between the nth partial sum and the n-1th is just one single term, a sub n. And thus, using properties of limits, the limit as n goes to infinity of that nth term, so specifically the term of the sequence, is equal to the limit of the difference between those two partial sums. And since they equal the same thing, limit properties tell us that the limit of both is going to be L minus L, also known as 0. So we can draw our conclusion as what we see right here, which is that the terms of the sequence in question that are being added up to create this infinite sum must approach 0, assuming that our series converges. So if we're trying to, I don't know, I'll try to be cool here. Oh shoot, I'm trying to be cool and I'm already messing it up. The TLDR, oh, I hate that phrase, but whatever it is, if that part just didn't work for you, what this is saying basically is that the terms of a convergent series, and sorry, I need to write this on multiple lines. So we're saying that the terms of a convergent series approach 0. So in other words, we can't say that they necessarily decrease, but we can say that their magnitude gets smaller and smaller as we go forward. That's the only way for us to have a series actually, or for the terms to behave in a convergent series. So having said that, having mentioned that, what I'm going to now present to you is something that follows directly from this theorem. The difference is it's been stated in a way that it's logically equivalent, but it's written in a slightly different way. It won't necessarily feel like it's the same thing. This next thing is the test that we're going to be using. This is what's called the term test for divergence. And I'll tell you right now that although this may not mean a lot to many of you, this is the contrapositive of that theorem. So that theorem we saw on the last page that we could prove and kind of conceptually wrap our minds around, that the terms' magnitudes were going to approach 0 as we go forward, this is the contrapositive of that, which is of course logically equivalent. It's true in the exact same way that the other one was. So in other words, it's always true. In this case, to get a contrapositive, you take your original statement, you reverse it, or invert it if you want to, and then you negate it. So this is exactly logically equivalent to what we saw before. In this case, though, it's framed in a way that's very easy for us to use to test a particular series to see if it converges or to see if it diverges. It says, if the limit of the terms of the series, or sequence, however you want to think about it, does not equal 0, and that doesn't just mean infinity, by the way. That means it could equal 1/5 or 42, God forbid. Then the series diverges. So basically this is telling us that if the terms don't go to 0, so if the terms of the series or sequence, however you want to think about it, don't go to 0, the series diverges. And I will say right now that this makes sense to me, but it took a while for it to finally sink in. So what I'm going to do is, rather than try to give you a proof on this page, or rather than try to give you an explanation without any context, let's just go do a problem show you the nth term test in context, and then I'll use that single example to explain what it is that we mean when we say if the terms don't go to 0, the series diverges, and to kind of confirm why it is that this works. And hopefully that'll be strong enough. I think it will be, but we'll see from here. So our next example that we're going to look at, or the first real one of the nth term test for divergence, asks us to determine whether or not this particular series converges. So we want to look at this series and see what we can conclude. And truthfully, it's possible with this nth term test for divergence that we might not be able to get an answer, but we should be able to tell if it diverges at least. So according to what the nth term test for divergence says, in fact, you know what, I'm just going to copy this here. Pardon-moi. No, it did not take the word nth, because that makes sense. Okay, let's do this. There's the nth term test for divergence. Let's put this in right there. Oh, it needs to be red. There we go. Looks like it was there the whole time. Okay, so what the nth term test for divergence says is if the limit as n goes to infinity of the terms of the series don't equal 0, then we know the series diverges. So what that means is, as we see here with this red line, what we want is we want to see what's happening to these terms as we approach infinity. So that's pretty simple. Like writing in here, I'll establish first that a sub n is equal to what's called the summand, the thing on the inside of the summation. So 3n squared minus 8 over 4n squared plus 2n plus 3. That will be our sequence. What we're interested in is what is the limit as n goes to infinity of that expression. So, and for the moment, I was going to steal that again. Sometimes I just want to blow that out. So close enough. So we want to figure out what is the limit of a sub n as n goes to infinity. And that's the same thing as asking what is the limit as n goes to infinity of this expression that we're looking at. Well, according to this, there's lots of different ways to evaluate this thing. We could use L'Hopital's rule twice. We could use controlling term analysis. Whatever it is we use to get here, the limit of this sequence, or this series, or this terms, is going to be 3/4. So basically we're saying the terms of this sequence approach 3/4. Now, if we're going to apply the nth term test for divergence, we need to look at that value we just found and ask ourselves one simple question. Is it 0? 3/4 is different than 0. So as soon as we see that, what that tells us is that therefore our series, and you know what, I'm going to stay consistent with this. Our series, I'll put it in red, our series diverges by the nth term test. So there it is. There's our conclusion. The series diverges, and it's using the nth term test. So now, having said that, like, you get the answer. I'm sure you're kind of nodding your head like, okay, yeah, that was pretty easy. We just took the limit, and then we went from there. But the question that should be in your head right now is, wait, what? Like, I thought that, what doesn't that mean that it converges? We got a number. Like, why isn't it converging? Like, that seems kind of awkward, doesn't it? Like, why is it that this didn't converge? And the answer is because what we just saw was what was happening to the terms. The terms of this series, not the partial sums, but the terms are uniformly approaching 3/4. So this is a little bit weird to think about, but what that basically means here, and I'll go to Desmos to confirm it as well, but what this means is that if we look at this particular series, I'll shrink it down here a little bit for us to play with. If that's our series, of course we know that this series is equal to a sub 1 plus a sub 2 plus a sub 3, and they all have value, of course, don't get me wrong. But what just happened was our work up here in purple, that indicates that if we were to analyze what's happening to the terms of the sequence and keep going further and further along, what happens is those terms get closer and closer to 3/4. So after a while, it's like we're adding 3/4 over and over and over again. Now 3/4 isn't exactly a large number, but the problem here is if you just keep adding 3/4 forever, what we get here is an infinite number of 3/4. So in other words, the value of that portion of this series would be 3/4 times infinity, because there's an infinite number of 3/4 because we have an infinite number of terms. And I'm hoping you're comfortable with the conclusion that 3/4 of infinity is infinity. So what that's showing us is, in fact, that this sum is approaching, and I shouldn't use an equal sign, I'll use an approaches. This sum is approaching infinity. It's got some finite value, and then we start adding 3/4 over and over and over again, which sends us to infinity, which of course tells us that it looks like our series diverges. So having said that, what we're seeing when we find out that the limit of the sequence, or the limit of the terms, maybe that's the best way to say it, the limit of the terms doesn't equal 0, is we're seeing that we're just going to keep adding some non-zero value over and over again. And if you want something to converge, it needs to go to 0, because otherwise you'll just keep getting bigger and bigger. Even if that was 3-4 trillions, it wouldn't get bigger and bigger very fast. But over time, it would still get bigger and bigger and bigger because we'd be adding up an infinite number of those tiny values. And that's exactly what we have in this situation here. Even though 3/4 is small, even though we just looked at like geometric series where 3/4 would be a great ratio, in this case, if we go on forever adding 3/4, because every single term starts to look more and more like 3/4, this is going to take us to infinity. Looking at it in a different way, let's pull up Desmos really fast and see if that actually agrees. So in this case, we'll put in our, oh shoot. Really? Okay, we've got, let's make sure I do this correctly. There's our series. Oh, I completely have lost it all. Okay, maybe I need to zoom out a little bit. There we go. So our series is 3n squared minus 8 over 4n squared plus 2n plus 3. Okay, so there's our work. Let's see what happens. Does it look like this is getting bigger and bigger as we go further and further on? Wait, I have minus 9, is that right? It's supposed to be minus 8, but it probably doesn't make a big difference, but we'll play it safe. So look at those sums. Notice it looks like it's getting bigger and bigger. It's continuing to grow at least. I mean, it's not growing very fast, but it does seem like it's growing. Let's go up to 1,000. See what happens here. It looks like it's getting bigger and bigger as well. There's just no slowing it down. It doesn't look asymptotic. Now again, too, sometimes when this happens, it could be that it's not asymptotic. It's just sort of like growing really slowly. But look at this particular series. Does that look like it's approaching an asymptote? That looks like pretty steady growth right there. In fact, as I start to zoom out, you're like, oh yeah, okay, yeah, it's getting bigger and bigger. It ain't going super fast. It's going very linearly almost, in fact. It looks almost like it has a slope of, I think, 3/4. But at the same time, clearly, it's not approaching anything. It's not as finite as some of the work that we've seen before. In fact, if I change that from a 2 to a nothing, look at how small that thing is. That thing starts to level off really, really quickly versus the other one, which didn't. So, having said that, like, there's something very important about the size of those terms. I did it again. About the size of those terms. We can't have them go to anything but 0 in order to converge. So in this case, by finding out that those terms were uniformly approaching 3/4, we see that, oh shoot, oh dip, there we go, use some good place reference. We find out that unfortunately, they're just going to keep sending the sum up to infinity because we keep adding that same small value. Now having said that, this is another one of those elements that can be confusing as well. So we've seen one example and I really dove deep into that example. Here's a second example for us to look at. We're told to determine the convergence of this thing, and your mind's like, cool, let's go look at the nth term test, and let's use it. So in this case, I'll pull it up one more time. Let's see what's actually going to happen here. So in your mind, you probably jump in really quickly. You identify, just as fast as the last time, that the nth term is going to be 3 over the square root of n plus 8. And then, of course, our tool for the nth term test is to analyze the limit as n goes to infinity of a sub n, which means we want to figure out what's the limit as n goes to infinity. In this case, of those terms, which are described by 3 over root n plus 8. Having said that, though, we can evaluate this really fast. No need for even L'Hopital's rule. We get 3 over infinity plus 8, and that is equal to 0. Now, having said that, sometimes people go and they think about the nth term test and they go, oh, it equals 0, that means it converges. Done. But be very careful here. It says very clearly in our statement that this is the nth term test for divergence. I could change it to black to emphasize it more, but I'll go right there. End term test for divergence. So this only tells us that something diverges. So in this case, by figuring out that it's equal to 0, our conclusion is instead not that this series converges, but that this test is inconclusive. Basically, this is a one-way test, like a one-way plane ticket that only takes you there, doesn't bring you back. This 0 value tells us that this is inconclusive, or specifically the end term test is inconclusive. So the reason for that is, all this says, this 0, what it's telling us is that our series, which again I'm going to cheat and copy here, what we're seeing is evidence that this series has the chance to converge. So in other words, I'll say that it might converge. It might, rabbit, it might. So it could converge, but we don't know for sure based on the nth term test, because the nth term test only works for divergence. So all we have is the possibility that this converges. And by the way, if you're curious, this series actually diverges. It just happens, it just creates this sort of false situation where people feel like the nth term test has decided something for them. So please be very careful. Make sure that you're only using the nth term test to determine divergence. In those situations where you get 0, unfortunately, it just means you have a candidate to converge. Unless, of course, it's geometric, in which case we have other tools that we can look at. So having said that, this is the nth term test. As we saw, it starts with a theorem that makes some pretty good intuitive sense, which is that if a series converges, then its terms have to go to 0. From there, we use the contrapositive of that theorem to declare what we use as the nth term test for divergence, saying that if the limit of the terms don't equal 0, then the series diverges. And our first example kind of illustrated why that was. No matter what that sum goes to, if the terms approach some finite non-zero value, that means you're adding up an infinite number of those terms, which means that your sum is going to naturally bloat up really quickly, and you're going to end up with a divergent sum, or an infinite sum, depending on how you want to think about it. And then finally, we closed up by talking about the inconclusive possibility, almost like a false positive, of the nth term test, where you get 0, which seems like a success, but it really just tells us that we have a candidate for convergence. We can't say for sure that it diverges. We can't say for sure that it diverges, just that it might converge. It's still a candidate. We don't have enough tests for that. We will have tests for it very soon. Don't you stress. Probably, I think the next lesson kind of covers that. But having said that, nth term test very narrow in what it does. So from here, having brought up all that information, I want to give you an opportunity to try some things using the nth term test. I'm trying to, you'll probably notice if you're thinking about like the questions that I ask in this particular try it, you'll probably recognize really fast that I'm being very specific here. I'm trying to develop your understanding on a conceptual level of what's going on with the nth term test. So particularly in question 1, I ask you a question about the sequence, and then I ask you a question about the series to really distinguish those two things. Because in my reading on the last few years, I think that's where a lot of students get confused. I think that they just kind of merge those two words, and it's understandable. I make that mistake too, and this is kind of its own domain of calculus separate from derivatives and integrals all the time. Having said that, though, I think these are some good problems to try. I highly recommend you try these. I think it will help cement the concept for you, and of course the problem set should as well. Having said that, that does complete the lesson for what we're going to be working through today. As I said, this was just 2 separate tests, the geometric series test, or how to tell if a geometric series, an infinite geometric series converges or diverges, and then what we call the nth term test for divergence, which allows us to use the limit of the terms of the series to see whether or not a series might automatically be disqualified and diverge right off the bat. So hopefully this has been a helpful lesson. If it hasn't, let me know what I can do differently, and I'm happy to try to make adjustments. I'm usually recording, I've got a pacing I'm keeping my pace of recording 1 day ahead of time, so I'm going to keep trying to do that as well, so that way I can answer questions. Also, as a reminder, these try-its will have answers posted. They'll be posted in the Google Drive. I'm going to put answers to the try-its from now on, as well as the original ones in the Google Drive, in case you want to check and see written work, rather than just check your answers using the Google Forms. And hopefully that'll be helpful too. Thanks to Johan for mentioning that idea and kind of helping me realize that was kind of a silly thing for me not to include it anyway. And again, since we're going to be indoors and kind of limited for quite a while here in Sacramento County, again, please stay safe. keep washing those hands, follow those 5 things we mentioned on Google yesterday, and stay patient. Like, again, hopefully this is kind of a helpful thing, giving you something to kind of work on, think about, and be productive with. If it's not, put it aside for a little while, but I'm hopeful that it will be. And hopefully there's some positivity in having this small connection, even if it's just me talking through a YouTube screen. It feels that way for me. I definitely feel better doing this and answering questions when I can. So, weird stuff. Yeah, that was awkward. Okay, thanks for watching. See you tomorrow. Well, sort of see you tomorrow. Have a good night.